Hello, this is Tom. Today we're doing our next class in the Science and Christianity series. Um, it is called Electromagnetism, Light, and Relativity. And hopefully these terms will become more clear as we go along. But I do want to call your attention to one of my favorite verses that we see on our first slide here from Psalm 36. It says, "For with you is the fountain of life. In your light we see light." Light is very special. It's how we physically see objects, but it also gets across the idea of understanding. And I think studying physical light, we're going to come to understand a lot more about physics than we have before. So let's get started. Before we get too far into it, um, I just want to review the ideas that we've developed so far. We've picked up the historical, um, um, development of physics. We've been able to explain the solar system. We see that Aristotle's ideas have given way to Copernicus, Kepler, Galileo, and finally Newton. Mathematical physics has become the hammer for every nail. Newton thought of light as particles. Another scientist named Huygens, we briefly discussed, thought light actually was more like waves that move, like sound waves or water waves or other kinds of things that kind of oscillate back and forth. We saw that Dalton was able to make sense out of chemistry by discerning atoms, and the periodic table started to develop. And we also saw that the physics of thermodynamics started to come along and help the whole industrial revolution to occur. So that's what we've covered so far. Today, we're actually going to we're going to pick up a different thread in the story of physics. And to do that, we have to look back briefly. We're not going to spend a really long time back in the past, and so we'll quickly catch up to where we were in the flow of ideas. So we pick up our story with magnetism and static electricity. Um, People have observed magnetism for a long, long time. At least by the 6th century before Christ, natural magnets, which were also known as lodestones, have been discovered. By the 11th century AD, if not earlier, people had figured out how to use the behavior of natural magnets to navigate. The key thing about magnets was that they seemed to point in a particular direction. They had a directional tendency. So what we call the North Pole of a magnet is called that because indeed one side of a magnet tends to want to align in the direction of what we call the North Pole. Now the behavior was known, if not understood, but they were able to use what they knew to help them navigate. Also, we we have the idea of static electricity um, coming about. I mean, the Greeks found, and perhaps other people found it too, that static electricity occurred when they rubbed amber together, or they rubbed amber with fur. So amber was like a pine pitch that had dripped down and solidified. The Greeks liked to make jewelry out of it, so you could just imagine that they would cut out some amber and shape it, maybe, like wear part of it away until they got the shape they wanted, and then shine it up real nice with some fur. They discovered that when they rubbed amber with fur, that the the amber took on a special quality. Like if there were any small feathers or anything lying nearby, the amber could actually attract the feathers. Um, Now, it didn't always seem to work, depending on how humid and everything it was. It seemed to be kind of chancy whether or not it would happen or not. But they noticed that it did happen sometimes. They didn't notice any connection whatsoever with magnetism. They didn't understand either one of these things. But so for a long time, people have known about magnetism and static electricity occurring in nature. Well, let's jump all the way forward to 1600. There was an early scientist, an early physicist named William Gilbert, and perhaps we should also acknowledge that he was a physician as well. He actually was Queen Elizabeth's physician from the year 1601. He was fascinated by magnetism, so he made a number of discoveries. Okay, he discovered that if you cut a magnet in two, that you wouldn't end up with two half magnets. You know, one with a north pole and one with a south pole. You would actually end up with two magnets, and each magnet would have a north and a south pole. You couldn't get just one pole by itself. Um, he also found that he could create magnets. Um, if he had hot iron, so imagine he went to his local blacksmith, and so if he took a really hot iron and had it hammered on, um, and also had it aligned from north to south, when it cooled off, he discovered that a magnet was created. Okay, now no doubt he knew that natural magnets pointed north. I mean, that's kind of the behavior that magnets proved useful for. So I don't know quite how he made the leap to this experiment he did, but he found out how to create artificial magnets. And he also thought about magnets, and he reasoned that because north poles of magnets repelled each other and south poles repelled each other, but the north and south poles of different magnets would attract each other. And because we also see that magnets line up so that what we call the North Pole faces north, he reasoned the Earth itself had to be a type of magnet. And of course, he was right about that. He also guessed that the Earth itself must be made largely of iron, and that's not a bad, that's not too far from correct either. Um, he was so enamored with magnetism that he started to wonder if maybe magnetism even explained the motion of heavenly bodies. Now remember, we've jumped back in time. This is still before Newton came on the scene and published his Principia, the laws of motion and his definition of forces and everything. But basically, Gilbert thought that maybe magnetism was the force that caused the motion of heavenly bodies. So he was ready to push his theory, and that's a pretty creative guess. That turned out to be wrong. Still, like the Greeks and any earlier folks who knew about magnetism, he didn't know why magnetism happened, but he knew that it was a real thing. Now, he also studied static electricity. Um, he found that not only did amber, which by the way in Greek is called electricus, not only did amber have this special property that if you rubbed it or something, that it could attract small pieces of feathers or whatnot lying about, but he discovered that other materials had similar properties. So it wasn't only amber that behaved this way. He argued that magnetism was something entirely different from static electricity, which was consistent with how people had thought about it up until that time. And that turned out not to be entirely correct, and we'll see that today. He also theorized as to why static electricity worked. Okay, and his thought was this: that maybe when you rub something, right? Maybe when you rub something, you rubbed off some sort of special substance from the material, which kind of wanted to return, okay, to the material, and it was that thing that quote, wanted to return that caused little pieces of feathers or other things which had that same material still to be attracted to the thing that you had kind of rubbed, like the amber or whatever that was. And that's insightful. It's kind of simplistic in some ways, but again, not entirely wrong, and we'll discuss that more as we go today. Now, interestingly, William Gilbert invented the very first electrical measuring device. It was an early device we call an electroscope. Okay, an electroscope is something that responds to a static charge. Okay, now it's a beautiful instrument. Here we have a picture of it. Let's talk about what it did. Okay, if he had a material that had static electricity, like because he had rubbed amber or something similar to amber, and there was a static charge, this device here, which was like a brass arrow, would actually point in its direction. Okay, so this thing would register the presence of static electricity by pointing in its direction. And I just want to remark, this thing must have been meticulously crafted by tradesmen during the day. You must have had people who knew how to work with brass and metal, crafting this arrow and the base. And there was a little pin that the whole thing rested on, and it was free to pivot. So it's interesting that Gilbert could have come up with this idea. Now, he had a guess that the static electricity in an object would attract things, and so he kind of guessed that maybe it would attract his little arrow in his early electroscope. By the way, it was called a versorium. And it did work that way, but he didn't really understand beyond that why it worked. And again, as we go further on, we're going to return to this topic and try to do it more justice. I should point out, because I think it's fun, the name versorium that he gave this thing comes from the same Latin word that we see in the phrase vice versa. So the versa means to turn around, to switch something around. And so this thing that was an arrow, it would turn in the presence of static. And so he called it the versorium. But it was the first thing that would constitute an electrical measuring device. It pointed toward static electricity that was nearby. Well, we also have Stephen Gray. So he came somewhat later, and now we've crossed the line. We've gone past Newton. He discovered that electricity could actually flow. Okay, so Gilbert seemed to think that you could take something out of the amber or amber-like substance that wanted to go back, but Gray found that once there was a static charge, certain materials would allow that static charge to transfer from one place to another, and he called those materials conductors. So, for example, copper. We make wire out of copper because of this very reason. It allows charges to flow from one place to another. There were other materials that did not have this property. For example, ceramics, and he called those materials insulators. And he did a little more theorizing about what was actually happening with static electricity. He thought of the charges or the static electricity, the thing that Gilbert had referred to. He thought of it as a fluid that could actually flow. And you see how that fits his observation about conductors. So he thought there was some kind of fluid inside of a material that could flow along a conductor. And you know, if you if you actually tried to create static electricity on a number of different objects, eventually you would find that sometimes objects that both had a static charge would attract each other. Sometimes they would repel. So kind of like similar to the magnets where you had a north and south pole, you seem to have two kinds of static electricity. And he thought maybe there were two kinds of fluids that could flow, and that maybe static electricity was if you lost or gained, you know, either type of fluid, so you had an imbalance there, that then you would have something with a static charge. So he turns out to have been correct there, and we could use that understanding to explain the versorium. But before we do that, let's go to one more scientist, and this one's going to be familiar. Benjamin Franklin, the first American to enter our study of physics. He was really fascinated with electricity. Now, he did not quite agree with Gray. He thought that you could he thought there was only one kind of static electricity or static charge, what we call static electricity. He thought there was only one type of static charge, and that if you had too little, you would have a negative amount of it, and if you had too much, you would have a positive amount. So it actually would work to explain all the same behaviors that Gray and Gilbert had noticed, but it was a simpler explanation. It turns out not to have been correct, but that's why he called the different types of static charge negative and positive, because he thought one was a deficit of some kind of fluid that could flow, and the other was some kind of excess of fluid that could flow. Well, even though his idea was not correct, and it turns out that Gray's idea was correct, there were actually two different kinds of static charge, positive, which we still call those two kinds of charge positive and negative, because for all practical matters, Benjamin Franklin's ideas work to explain how things behave, and so the terms stuck. Ultimately, Gray was correct. There were two types of charges, of static charges, but they were called negative and positive. Benjamin Franklin thought it was a deficit or an excess of one type of charge. That's not true, but still the terminology stuck. Now, one thing that Benjamin Franklin did anticipate and was correct about is that the sum total of all these charges stayed the same. So if you took a piece of fur and rubbed amber, you might cause some charges to flow from the amber into the fur, or vice versa, but they would go somewhere. So you kind of normally have charges that balance, and then if you have static created, whatever positive charge you end up putting on one object, you end up with a corresponding negative charge on the other object, so that it still adds up to a neutral charge. So now Benjamin Franklin also famously wondered if lightning was related to static electricity. Okay, he was not the first to wonder about this, but you know, even if you occasionally see a static spark, it's like a very small, you know, like a very it's like a microscopic example of lightning. It kind of looks like lightning a little bit, so it's not too unreasonable for people to have wondered, hey, I wonder if lightning is somehow related to static electricity. The thing about Benjamin Franklin is he was the first to demonstrate that lightning was related to what we call static electricity or static charges. And he flew a kite way high up in the atmosphere. Um, Lightning did not hit the kite like is so often thought, but he got the kite high enough up so that that it was in a region of the atmosphere where there were where there was a static charge, and that static charge was able to be conducted down to the ground on his wet kite string, and he had a key, like a metal key, hanging on his kite string, and he was able to impart himself a static charge. I don't know that Benjamin Franklin risked himself too much. I think he actually had like a teenager who worked for him, or a young, maybe a younger boy who worked for him, um, doing part of the experiment. But he was able to demonstrate this way that lightning was in fact related to static electricity. Now, this led to one of the very first inventions that had a practical application related to electricity. Um, it combined his insight in his demonstration that lightning was related to static electricity with what Gray had come up with, that that charges can actually be conducted along a suitable type of material called a conductor. And so he put a high up on a structure, what we now call a lightning rod, a piece of metal, and he connected it to the ground with a conductor, so that if lightning tried to hit the ground, or hit a structure, that it would actually hit the lightning rod, and it would be quickly routed to the ground by the conductor, which was a material that did a good job conducting these electrical charges. And that worked. It was actually a significant problem. A lot of structures burned down during that period of time because of lightning strikes, and the lightning rod proved successful at preventing that type of fire in a lot of cases. Well, so now we're ready to explain the versorium. Um, it's made out of a conductor. It's made out of brass, a good conductor, that allows charges to flow. Let's suppose that we bring an item with a positive static charge near the arrow that points to the left. What's going to happen? Well, because the negative charges attract, because the positive charge of the object that's not touching the versorium, because the positive charges attract negative charges in the versorium, right? Those negative charges will actually flow into the left toward the little arrow at the end of the versorium. Okay, that means that to the right, okay, there's the negative charges are depleted, meaning you'll also have an imbalance there. You'll have a net positive charge there because what's left are the positive charges in the object. So because we brought an object with a positive charge near the left end of the versorium where the arrow is, and because negative charges are attracted to that end, that means the arrow on the left ends up being negatively charged, and it's attracted to the positive object that's nearby. The tail of the arrow, which has a positive charge, is repelled by the object, which has a positive charge, and so the tail of the arrow is going to want to rotate away from the object. So the object tends to turn in the direction of the object with a static charge. If the object we brought over had a negative charge, the opposite thing would have happened. Now, you might think, or it's actually a little bit different. You might think that positive charges would have flowed, but it turns out there are two types of charges, but only the negative charges in an object flow freely, like in a metal, in a normal metal object anyway. Under other cases and under other conditions, positive charges can flow too. But so if we had brought over a negatively charged object toward the left near the tip of the arrow, the negative charges in the versorium, the brass in the versorium, they would have tried to get away from the negative object. They would have flowed into the tail, leaving a net positive charge in the arrow, which would have been attracted to the negatively charged object, and the tail, which now has a negative charge, would have been repelled from the negatively charged object. And so the arrow would tend to want, the front end would want to rotate toward the negatively charged object, and the tail would want to rotate away. So once again, the arrow would point in the direction of static electricity. Now, this was a very crude device by our modern standards, but it did point out the existence of a static charge. Later on, things got fancier. So as ideas developed, eventually people figured that they could not only measure the existence of the static charge, but they could also measure a how strong a static charge things were. And so how that happened is there were many variations on this, but how I'll give you an example of how that happened. So like an early electroscope that allowed you to measure the strength of a charge involved like a little piece of gold leaf foil that was against a little piece of brass inside a little device that was closed off from the air by glass, so that like breezes and things wouldn't affect the measurement. And so if you brought a charged object near the top of this thing, which was attached to the brass and the foil inside the little dial, the charges would the negative charges would either flow into or out of the the brass and the foil inside the dial. And what would happen then is both of them would either have a net positive charge or net negative charge, and the little gold foil would repel the little brass strip that it rested against, and so it would be free to move, and it would move away at a certain angle. And here's where Newton's laws will come into effect. You could figure out, based on the weight, the mass really, of the foil, and given the fact that gravity pulls things down, you could figure out according to the angle that the little foil made compared to the little vertical strip of metal, the angle would tell you how strong the force was that was pushing the foil away from the brass strip. And that became a measure of how strong the static charge was. So then we would have electroscopes not only identifying that there was a static charge, but they would also be measuring in some ways the size of the static charge. And the way they would do that is by using Newton's physics to basically figure out what amount of force the foil was being pushed away with in order to balance with gravity so that it would hang at a certain angle. We see a picture of that, happening here. Like if you even brought like something with static charge, like a rubber comb, you maybe combed your hair and it had ended up with a static charge, and you brought it near the electroscope, you would see this behavior. You didn't have to touch the electroscope for this to happen. If you just brought it near, it would work in the same way that the versorium worked. But if you actually touched it to the top of the electroscope, the charges, some of the charges would actually flow from the comb into the electroscope, and then you would be left with a charge. So even if you move the comb away, you would see that there was a certain amount of charge remaining. And so that's where the word charged came from. If you actually allow the charges to flow into your device, you would say that it was charged up. And eventually, if there's human stuff, the charges actually can drift away. So eventually, you would have lost the charge, and the term used was it would have discharged. Well, it turned out that that this idea of being able to store a static charge was very appealing to early scientists, during this era. And so at some point, there was a variation on this basic concept that came to be known as a Leyden jar, because it was invented in the city of Leiden. And it kind of looks a little like an electroscope, except no one's measuring charges with this thing. What happens is there's a conductor that actually runs to the inside of a layer of foil inside a glass jar. And typically there was also a layer of foil, tin foil, on the outside of the jar. So what happened is, if you brought a charged object and touched it to the Leyden jar, the charge would actually flow down the conductors all the way into the foil inside the jar. The fact that there was a lot of conductor here for the charges to distribute themselves along made it very capable of storing charge. Because remember, the charges, the like charges, like the negative charges, repel each other. So the more conductor they can spread out on, the happier they are to go there, which is why they leave the comb or whatever other object with a static charge is brought to it, and why those same charges flow out along the conductor. So why is there conductor outside the jar? Because it turns out that inside the conductor on the outside of the jar, you can also have charges flow. So let's say we charge our Leyden jar with like negative charges. So negative charges distribute all along the inside. As that happens, on the outside foil, outside the jar, the negative charges in that foil will actually try to go away from the bottle. And so the side that's actually touching the outside of the jar would be left with a net positive charge, and on the outside of the foil, you would have a net negative charge. So that would make it easier for the foil on the inner side to receive the negative charges, because nearby there were nearest to that foil on the outside foil, you would have a positive charge that was attractive to those same negative charges. I know it's a little complicated, but the main thing is the charges would flow and try to distribute themselves. So this allowed charges to be stored up for the performance of experiments. And also during the Enlightenment, actually a lot of party games were based on these Leyden jars. So I guess people administered different shocks to each other inside social gatherings, and they thought that was just nifty. So, but before before our modern era, I guess that was quite the hit. Now, basically what we're looking at here is a battery. It's something that stores up charge, so that if you wanted to, you could hook a conductor back up to it and get the charges to flow somewhere else. In fact, if you had a number of these things wired together, the original term for this was a battery of Leyden jars, because a battery A battery, the word battery at that time referred to a whole bunch of cannons or something on a ship, like a battery of cannons. So instead, you had a whole bunch of lined jars in a row that could administer a bigger and bigger shock instead of shooting a cannonball. So the name battery came to came into came to be applied to this situation. Now they noticed two things. Early experimenters, they noticed that if you ran conductors between the top of one line jar and the outer foil on another line jar, and we call that in series, that you could get bigger and bigger sparks, bigger and bigger shocks. Whereas if you wired the top together, the tops of the line jars together, and you also wired the bottom of the line jars together, as pictured here, and we call that in parallel because all the tops are together and all the bottoms are together. Then you would not get bigger sparks, but you could get longer static discharges. So this was the first item that functioned like a battery. In the modern world, things that still do this kind of thing in electrical circuits we call capacitors. But it was the first type of battery that existed. For early scientists to play with and to better study electricity. Well, observations come from all over the place. So there was a riveting discovery by a scientist named Galvani in Italy. During this time, dissecting frogs was something that anyone studying medicine would do in their schooling. So this Galvani guy discovered when he was dissecting a frog that if he happened to touch two different parts of the dissected frog's body with two different types of metal, not the same type of metal, but two different types of metal, he noticed that the frog leg actually jumped. Okay, and so it was guessed that this was yet another example of electrical charges in motion. And from that, Italian scientist named Volta, which is where we get the name volt today, noticed that indeed, if you didn't have to have a dead frog, if you took two different types of metal, say zinc and copper, and you put suitable material between them, like a damp cloth, maybe soaked with seawater, that you could also, by hooking wires to either end of it, get charges to flow. And each one of those we would call a cell. And you could stack as many of these as you wanted together, and you could and we would call that you could put these cells in series, and you could get higher and higher, bigger and bigger sparks, which we call higher and higher voltages. And so what was really good about this was the whole technology of line jars could only store up enough charge to flow briefly. So, and they didn't even work very well when the air was humid. These sorts of cells hooked in series could create as big a voltage as you wanted, as big a spark as you wanted, and the charge could flow for a long, long time. Okay, so really, this is the discovery of this discovery allowed static electricity, or I should just say electricity, flowing electricity to occur, and to occur for periods of time and to be studied and experimented with and everything. So it was really crucial in the development of an understanding of physics, and the insight that the frog legs triggered from static electricity or static discharge, or you know, electrical spark, um, that was an important discovery on its own, because it showed that our nerves actually work by charges traveling along them. Okay, but this is the first chemical generation of electricity. Now this is very similar to how our modern batteries work. Um, if you look at a traditional car battery, a lot of times you will have like two different types of metal or conductors, and they'll be in actually in a liquid uh, situation, but they also work in just the same way. We some batteries have liquid, some have kind of a moist um, material inside of them, like the kind of batteries you buy from stores, that are not that different than what Volta came up to. So eventually, this leads us to modern batteries, and we see here how basically we've gone from a dead frog to a multinational rabbit. But yeah, this is the invention of batteries. So it was just a couple of short hops from discovering nerve impulses in frogs to modern battery-powered rabbits. Well, things got ever more studied as time went on. We eventually have a French scientist named Coulomb, and he's very interested in electrical and magnetic forces. Now remember, still people are thinking of these electrical magnetic forces as two different things. Okay, and they are in some ways two distinct things, um, but they're not considered connected. But here's what he did. Now that you're able to measure with electroscopes, and some of them got ever more clever, so you can measure better and better, he's able to measure how the electrical forces between charged objects change depending on how far away one item is from another. And he did the same thing um, with magnets. But what he found when he measured electrical forces is that if you doubled the distance between things, you only had 1/4 of the force between them. The force of attraction or repulsion was only 1/4 of what it was. If you tripled the distance between them, the attraction or repulsion was only 1/9 of what it was. Okay, so he was able to measure he was able to measure the size of the charge, and then given the size of the charge, he was able to measure how the distance affected the attraction or repulsion. Just using Newton's physics and the laws of motion and the understanding of the force of gravity to compute, what the force of attraction or repulsion was between these charged objects. So he summed this up in what we now call Coulomb's law. The force between of repulsion or attraction is basically proportional to the size of the charges in this little formula. The charges are referred to as Q1 and Q2, divided by the square of the distance between them. Okay, and this K thing here, this K is just what we call proportionality constant, something that doesn't change if you change the charges or you change the distance. It's just always a particular value in that formula. And I just want to ask you guys, does this look familiar at all? Well, if we remember back to gravity, Newton's universal law of gravitation, we had exactly the same kind of thing there. Instead of Q1 and Q2, we had big M and little m. But things attracted gravitationally according to the inverse of the square of the distance between them also. And there was also a proportionality constant between them. So the force of gravity was proportional to the size of the masses divided by the square of the distance between them. when it came to electrically charged objects, the force between them was proportional to the size of the charges divided by the square of the distance between them. So these two formulas mathematically are exactly the same, exactly the same, and also magnetism works this way too. Coulomb showed. So that's very interesting. Mathematically the same. The constants of proportionality are different. And, you know, like with charges, it depends on the size of the charge, not the mass. Whereas with gravity, it depends on the size of the mass. But mathematically, they're the very same thing. So is that a stunning coincidence? Or is there something underlying that causes it to be this way? Well, um, we can also point out another similarity between the study of gravity and the study of electrical magnetic forces. Coulomb also used to make very fine measurements. And that allowed him to determine what that constant of proportionality was. He also used the torsion balance, um, as was used to discover the proportionality constant for gravity. So that allowed him to figure out the K in the formula. And so you could just use the formula to figure out what the attraction would be between charged bodies. Okay. Um, so this was quite an important discovery that charged objects attracted like this, that magnetic forces kind of, have the same kind of relationship. Um, but as brilliant as his work was, Coulomb did not understand why things work this way. So um, he he and although we have a great symmetry here between the formula for gravity in the formula for charged objects and how they attract, and the formula for magnetic objects, he did not uh, he did not have any theory he put forward as to any relationship between these forces. In particular, he didn't relate electrical and magnetic forces, even though they seem to behave in the same fashion. Um, it turns out that when he measured the electrical and magnetic forces, that constant of proportionality was much, much bigger than the constant for in the gravitational formula, the big G in the gravitational formula. In other words, electrical and magnetic attractions were so much stronger than gravity. So here we have a fun picture. Here we have a fun picture, and now we know that electrical and magnetic forces are in fact two expressions of the same underlying force, which we call the electromagnetic force. And our big muscular guy on the left pictures the electromagnetic force compared to the force of gravity, the kind of the skinnier guy on the right. Notice the electromagnetic guy looks much stronger, right? But I will just point out, and this is for a later class, that even though he looks weaker, the figure that's supposed to stand for gravity, he has a pocket watch there strapped to his shorts. And so it's going to turn out that gravity may not be as strong as electromagnetism, but gravity knows what time it is. And I'll hopefully explain that in a future class. By the way, um, we have now uncovered in our study two of the what we call the fundamental forces of nature that explain everything we see in nature, how everything relates in nature. But we're not quite done. Eventually, we're going to come to a few more. So I just want to point that out now. Well, we keep noticing similarities between electricity and magnetism. At some point, um, it began to be observed that there was indeed a connection between the two. So um, there was a um, there was a scientist named Oersted who discovered that an electrical current flowing near a compass, like through a wire, say. So you got your voltaic cells all stacked up, nice strong current flowing through a wire. If you put that wire through near a compass, it actually causes the needle of the compass to deflect. In other words, he discovered that an electrical current caused a magnetic field. So it was a whole new way to generate magnetism, which was of great practical importance. But as far as science was concerned, it was very intriguing because it pointed out there was indeed a connection between flowing charges and magnetism. Well, it wasn't long from there that other people took um, his observation and they discovered how to make electromagnets by wrapping a wire around and around and around, um, like a empty cylinder, or even like a nice cylinder of metal. So you could create what we now call an electromagnet that way. The if you actually put iron in the middle, it would actually be stronger. And so it seemed to be that the magnetism created by each loop of the wire, the more loops, the stronger the magnet for a given flow of current, um, would cause the iron to become magnetic, and then you would have the combined magnetism that would be stronger. So all of this was used to create telegraphs and practical electrical motors, all those kinds of things. So the research was broadened and, um, understood more and more mathematically by a guy named Ampere. That's where we get our measure of current from these days, the amp, right? He published a book in 1826 on electrodynamics. Later on, someone that we're going to come to in today's class named um, uh, Maxwell, James Clerk Maxwell. I got the name wrong there in the slide. He's going to refer to Ampere as the Newton of electricity, but I think he was being humble because I think Maxwell was the Newton of electricity. But yeah, so he made a big contribution. Well, we have at this point our occasion to meet another scientist who came along, early physicist, and his name was Faraday. Okay, now Faraday actually started out um, in chemistry because his mentor was named Davies, and Davies studied chemistry, which had come along from Dalton. Um, but he ended up being very fascinated with electricity, and he reversed the idea that a flowing current created magnetism. He showed that the opposite could be true, that you could take a magnet and you could create electricity, flowing charges inside a wire with a magnet, so it was reversible. And so if you cause a magnetic field to move inside a coil of wire, it would actually create electricity. Now there are many similar, the general behavior, um, um, could be arranged and could be achieved in different ways. But Faraday created the first electrical generators. So you could take you could take mechanical motion, whether it was steam powered or horses or whatever, or a human turning a crank, and it could move, it could cause something to move so that a coil of wire would see a changing magnetic field, and from that you could actually generate electricity. Faraday, I guess everybody who likes electricity owes him a debt. Faraday also created the first example of an electric motor, but it was very impractical. Okay, eventually people improved the electric motor, but let's just camp out on Faraday for a bit because he is a very important figure. Um, he um, he made some other interesting discoveries. One of the teases that he also noticed was that if you if you took light that was polarized, okay, now we haven't talked much about polarized light, but if they understood that that light would like if you pass light through certain crystals, it might be bent differently, and the behavior of how the light was bent by certain types of crystals. Um, kind of like a prism, except a prism that treats light differently depending on the type of light. The direction the light bent in was called polarization. Some light would tend to bend one way, some light would tend to bend the other way. What Faraday noticed was that um, the polarization of light could be affected by magnetic fields. Okay, so you know. Um, that suggested that there was a connection between magnetism, which was connected to electrical charges, between magnetism and light. Okay, and light seems totally different than magnetism. Light seems totally different than electrical charges. Light is a very different thing, but we're going to see how um, this hint came to be more than a hint. It came to be understood as a fundamental connection. Um, so it's kind of interesting, but Faraday had no idea why that was. Perhaps the most important thing that Faraday did was he helped to visualize um, the forces that came from electrical and magnetic um, attractions as what we call fields. Okay. Now, we talked, I think, earlier about gravitational fields. The idea is no matter where we are in space, no matter where we stand on Earth, on a chair, on our bed, on the floor, up on a mountain, every place we are, we experience a certain gravitational attraction to the Earth. Even if we went out in space, we would experience a certain gravitational attraction to the Earth. You know, if we move fast enough, kind of perpendicular to it, we might be in orbit, but still that attraction would keep us in orbit. Okay, so the fact that we have a weight everywhere, that there's a certain amount of force attracting us to the Earth, we call that the gravitational field of the Earth. The idea of a field is that no matter where we are, there's a value for how big that attraction is. We can also think about when it comes to electrical forces, like forces of attraction between like or unlike static charges, or between magnetic forces, we can also think that those forces have a value. So if you have two magnets in relation to each other, like if you're considering one magnet related to another, no matter where you move that magnet, it experiences some amount of force, even if only zero, but it has some value for the force that it experiences no matter where it is. And so there's a certain amount of force, like how much force there is, and there's a remember, force is a vector, so there's also a question of what direction the force is in. Okay, so Faraday really, really studied, um, you know, electrical forces and magnetic forces, and he illustrated them in diagrams that kind of pictured the field as a whole. So in some cases, he didn't actually draw the field so much as he captured the fields. One of the really clever things he did was he took a magnet, and on the magnet he put a piece of paper, and then he scattered these very fine iron filings. But before he scattered the iron filings on the paper, underneath which was a magnet, he actually put a coat of hot wax on the paper. And when he sprinkled the filings on the paper, they lined up according to the magnetic field, because the magnet's magnetic field caused the iron filings to also turn into little magnets, and they pointed in the direction, like the north end of each filing would point in the direction of wherever the magnetic field was pointed north, or it pointed in the direction of the magnetic field from the underlying magnet. And when the wax hardened, when the wax cooled off and hardened and became solid, the image was left. So he was able to even take the piece of paper, remove the magnet, and let and then he would have an image of what the magnetic field looked like related to that original magnet. So he noticed some things. He noticed that where the forces were strongest, where the magnetic forces were strongest, it was near the poles of the magnet. And the poles would be kind of, and away from the poles, the forces would be much smaller. They'd be kind of weak. He also noticed that the northern pointed magnetic field started with the North Pole, but if you follow the little filings, they would kind of form an arc that would loop back around to the South Pole. So what happened is the magnetic field of the original magnet would cause what we call an induced magnetic field in each of the little filings, so that it would kind of line up its South Pole with the magnetic field in one direction and the North in another, and so you could kind of map what these lines would look like in space. I think the visual picture probably shows what was happening there better than I can explain it. So now, Faraday captured the magnetic field on a flat two-dimensional piece of paper, but really these lines of forces were everywhere in space. So we can picture kind of rotating this magnetic field kind of 360 by rotating the paper around, and that's what the magnetic field would look like in space. Well, Faraday noticed that there were more filings clustered together where the magnetic field was stronger on each of the poles, and then it kind of spread out as you went away from the poles, and then it kind of got concentrated in together. So it turns out that how many filings were clustered together kind of was proportional to the square of the distance away from the pole. So it kind of corresponded to the strength of the force. Okay, if you thought about it in 3 dimensions. Okay, in 2 dimensions, it actually it was actually kind of proportional to the distance from the pole of the magnet. So he did similar pictures with electrical forces, and he measured the forces, both their size and direction, and he would draw the electrical fields on paper. He would draw these little lines that indicated the electrical forces. And this is where we can understand better why it is that all these different forces, gravity, electricity, and magnetism, they all kind of are inverse square forces. In other words, if you double the distance, they drop off by a factor of 4. If you triple the distance, they drop off by a factor of 9. And that's because you can kind of imagine that these lines of forces get ever more, spread out as you increase the distance away from whatever the source of the magnetic or the electrical force is. Okay, and so the number of lines actually going through, a particular region, which kind of correspond to the strength of the force, that spreads out accordingly. So the reason why we get these inverse square forces appears to be that, if you can almost imagine that the force kind of just spreads out over the volume as it goes, and over the, so that any particular distance away, you can kind of picture, the volume being enclosed by a sphere. That would be the size of the electromagnetic force at that region. So hopefully this picture here helps. So anyway, he drew many such diagrams. He studied all kinds of different cases. So like here's an example of two charges of the same sort, I think two positive charges. And if you measure the combined electrical field that those two charges cause, you get the lines of force that seem to radiate out from each of those little round places. So those are the charges, the A star and the B star, or the A asterisk, B asterisk, those are the charges. And the lines that radiate out from them, right, at least very nearby, those lines are the electrical forces that Maxwell pictured. And then we'll talk about the intersecting lines there in a second. But yeah, so this shows the electric fields, and it turns out that these other lines that are kind of perpendicular to those radiating lines, Maxwell called these equipotential surfaces. Okay, now here's why. Because just like in gravity, right, because we study potential energy, just like if you stand at a particular height, it doesn't matter where you are. Like if you're if you're on a table that's or let's say 3 feet off the ground, no matter where you are on that table, you have the same amount of potential energy. In other words, if you drop, right, if somehow you remove the table real quick and you dropped, you have the same amount of potential energy to do work, right, no matter where you are. And so that table we would call an equipotential surface. And if you went up on a higher table or a higher shelf or something, then that would be a new place where you'd have the same or an equal amount of potential. Well, these little lines that Maxwell also drew in, or I'm sorry, Faraday also drew in, they show where the potential is the same. So electrical forces, just like gravitational forces, can do work. Any force can do work. Remember, work is force times distance. So he also showed that if you traveled wherever, where at any point, no matter what the force was, if you travel perpendicular to it at that point, you're not actually doing any work. You're actually staying at the same level of potential. So he was able to draw this out. Now, all this to say, this introduces the idea of work and energy and everything into electrical and magnetic situations, right? So we bring those same concepts along. And when we talk about voltage, right, which we understand as a practical aspect of living nowadays, voltage is really a measure of electrical potential. Okay, so in his picture, these equipotential surfaces are pictures where you have the same voltage. Okay, that's what the pictures are showing relative to some other point. You have the same voltage. And so the only difference between our concept of potential energy that we had before and electrical, what we call electrical potential is how much potential energy there is per charge, right? So in a given electric field, right, the forces are really proportional to the size of the charge that the electrical field is acting on. That came from that formula in Coulomb's law, right? So for any item, um, like if you put it, the work that can be done is based on the force, which is proportional to the charge of the item that's being worked on in an electrical field. And um, the um, if you just wanted to measure how much potential there was for any charge, no matter what size it is, you would just say, okay, I know what the force is for this charge. I'll divide the size of this charge out, and that way I know what the relative size of the work that can be done on any charges on a given charge. And so then if you bring something else in, then you know how much work you can do on that. Anyway, this is really a picture of voltages based on the arrangement of static charges that Faraday studied. So Faraday's pictures proved to be very, very helpful for James Clerk Maxwell. And he is probably the most important physicist we have studied after the time of Newton. He made lots and lots of contributions to different aspects of physics and astronomy. But the main thing we care about today is he figured out how to describe electricity and magnetism with the exact same set of formulas. Clearly, they're interrelated. He was able to come up with a set of formulas that described any kind of electricity and magnetism. And the idea people the way people describe what he did was they say he unified electricity and magnetism into one set of equations. In other words, they could be understood at this just by looking at the same set of equations, and clearly they're interrelated. We've kind of established that. That's when people certainly started referring to electromagnetic forces or electromagnetism as a thing, not electricity and magnetism. But at this point, the two ideas were completely connected by mathematical physics. Okay, and here's the big surprise that Faraday got. Okay, he found that if you studied a changing current and asked what kind of electrical and magnetic fields it would generate, you end up showing that if you have a field that oscillates up and down, like what we would call alternating current, which naturally will come out of certain types of Faraday generators, if you studied the field that should result, you would get a field that also oscillated like a wave up and down. So if you looked at the electrical field or the magnetic field at a point, you would see that it would alternate up and down, just like a water wave or something, except we're talking about the strength and direction of, say, a magnetic or an electrical field. And if you put them both together, you would find that the electrical field would oscillate up and down, kind of perpendicular to the magnetic field. So there was so when you had an alternating current, it would generate this kind of electromagnetic field where the electrical and magnetic fields would be oscillating. You can picture them both together. And in fact, the math showed that this electrical, what we would say, this electromagnetic wave would even travel, just like a wave on a water. It would travel at a particular speed. And guess what speed it was? It was the speed of light. It was the speed of light. So Faraday immediately understood that there's no way the math would give the the speed of the wave, and it just coincidentally was the speed of light, because the speed of light itself had been measured. I don't think we've talked much about it, but they were able to apply their orbital mechanics and stuff from the understanding of that Kepler and Newton had given them, and they were able to observe the orbits of the moons of, say, Jupiter, and notice, depending on how far Jupiter away, that it would take us more or less time to see the moons of Jupiter. And then if we said, okay, well, how fast would light have to travel in order for us to account for the lag time there, we were able to discern the speed of light. They actually directly measured it, and I won't get into how they did that too. So this had been done by the time of Maxwell. And so when Maxwell put his equations together for electricity and magnetism, and he asked the question, what would happen to the electrical magnetic fields, he discovered that you would get a traveling electromagnetic wave, and it would travel at what just happened to be the exact speed of light. So he knew that now he had connected what we perceive as light to two seemingly very different things: electricity and magnetism. No one saw this coming. There was just a hint, as I said earlier, about the polarized light being affected by a magnetic field that showed there was some relationship. But this showed that light, in fact, was a traveling electromagnetic wave. That's what light was. So Maxwell speculated that maybe you could have, there's no reason from his equations why you would just be able to have light that traveled, in what we would call the visual range. He thought that maybe there were electromagnetic waves that would travel with far higher and lower frequencies than light traveled. And it was understood that it had been understood for a little while that light was a wave, and we'll talk more about that. A scientist named Young had shown pretty convincingly that light was a wave, putting to rest the great debate in physics up to that time. Was Newton right? Was light little particles, or was it like waves like Huygens thought? Young had shown, and we're going to discuss that when we get to our quantum mechanics, that light was a wave. Here, Maxwell shows that electromagnetic waves are light. Okay, and so it was understood that light waves had certain frequencies because that had been measured by this time using Young's work, and yet Maxwell speculated that but you could also have waves that had higher and lower frequencies that corresponded to our visual light range, and that turned out to be correct. That's where radio waves came from. As it was only a few years later where people tried to create such waves using alternating currents or sparks or other things, and they were able to. And the technology of radio broadcast was born. Eventually, we have microwaves, we have other things. So Maxwell actually opened the door to showing us that there was a large electromagnetic spectrum, and visual light was just a little tiny slice of that. So that was a pretty dramatic insight. Here's another picture that shows just how small a range our visual light has, and how much stuff, how many other types of waves there are, um, well beyond what we can see. Both higher and lower frequencies are bigger and smaller wavelengths. And actually, a second ago, I misspoke. Let's talk a little about how Young showed that light actually did travel in waves before Maxwell proved it mathematically. The picture before us on the right shows, say, a puddle with raindrops coming down. I'm not sure it's exactly that, but that's the kind of thing we would see if we see raindrops on a puddle. On the left is an experimental device that generates similar kinds of little water waves by having two little um, two little probes that can kind of bounce around and create little ripples in the water. What's interesting is water waves, um, you know, kind of generate patterns that can be explained by supposing that when two little ripples meet, um, they kind of get added together. So if you have one wave that's a little higher, if you have a wave that's higher, a little ripple that's higher intersecting another ripple that's higher, above the level of the water, um, the combination of the two, as the waves travel, get added together, so it's higher still. Whereas if you have a little ripple that's higher than the overall level of the puddle or the water, and it just happens to meet another little ripple that's dipping in below the level of the water, when you put those together, you also add the heights, but one of the heights is negative, it's below, so actually you see less of a wave. So the patterns we see when it comes to little ripples on a puddle or a pond, or even things that are set up in an experiment, same sort of thing set up in an experiment, you can explain them using Newton's physics and math, and you basically get this behavior which you can see. This is how waves behave. This is a characteristic behavior of waves. They add together, and physicists call this they say that that waves can be added together into a superposition. That's the word they use. Well, Young showed that light did the same thing. Instead of two little probes in an experimental apparatus generating two little ripples on a little tray of water or puddle, he showed that if you took a light source and you allow that light source at some distance away to travel through two little slits in a barrier, and then you observed further down, in this case to the right, on a screen, you looked at, you could even move the screen back and forth and observe the different patterns at different distances. If you looked on a screen, what you actually would get alternating bands of bright and dark on the screen. And the understanding here turned out to be that you had light waves. Okay, in other words, light waves work just like water waves. They added or subtracted depending on, if you were kind of positive or negative, a positive or negative wave of that type, and you could even tell from the spacing of the gaps, what the wavelength of the light is, and you can so it was able to be determined that visual light, of a particular color was a certain wavelength, and so they were able to see, that the wavelengths of the visual spectrum. They were able to even correlate that with, like, how light was bent by a prism, okay, to give the rainbow effect, or even by just a lens. So they were able to explain how different color light was bent slightly differently by lenses, And it turned out Maxwell's equations explained all that too. So Maxwell's equations show mathematically not only was light a wave, as had been seen experimentally by Young, but it also was able to explain why optics worked the way they did and why prisms caused light to be separated into its different colors, because the amount of bending that would happen as light went through a prism would vary, would be slightly different for different wavelengths of light. So Maxwell's equations explained all this, and so physicists were pretty convinced that yes, light was a wave, and that put to rest the whole particle wave debate. Well, um, that's not the end of our story about light, not by a long shot. Um, uh, Sometime in the late 1800s, around 1885, people started to study the light given off by different elements. Remember, chemistry is also happening, so they're starting, like it's starting to be possible for people to test, like, okay, what does hydrogen do? What does oxygen do? Things like that. So people start to understand that certain materials give off light only in certain wavelengths. Okay, so for example, here we see that hydrogen in the visual range just gives out light in certain narrow little ranges. Likewise, if you actually shine a broad spectrum of light through, like normal sunlight, and then you look at what changes if you pass that light through hydrogen, it turns out hydrogen will also absorb light in those same wavelengths. So this is something that Maxwell's equations did not explain. Now it turns out that just the fact alone proved very useful for astronomy, because helium was not even discovered on Earth. It was only discovered when people started analyzing the spectrum of light coming from the sun. There were certain lines that were missing, from the absorption spectrum in the sun, and it came to be figured out that those lines were for helium. And soon thereafter, the element helium was discovered on Earth as well, but it was discovered first in the sun. Well, this whole thing about just certain wavelengths being absorbed or given off by materials, by certain sorts of atoms or molecules, this was totally not understood, and so that was kind of a bit of a mystery that Maxwell didn't explain. But it ends up being very important later on when we study quantum mechanics. Well, at this point in our discussion, we start to get into what's called modern physics. A lot of times people call everything up until this point classical physics or Newtonian physics. Okay, but around the turn of the century, the turn of the 20th century, three revolutions hit physics. They were called special relativity, general relativity, and quantum mechanics. Okay, and we're going to discuss the first one today because it ties into our topic of light. Now, I just want to warn you before we go further, it can sound like some combination of science fiction and psychosis. This stuff gets pretty weird, but it's been well established as true by every experiment that's ever been done. So far as we know, these things are solid. Okay, so today we're going to, as I say, we're going to talk about special relativity. It is like the other two, bedrock, among the most tested theories of all time, and it just came out of nowhere. It fell unexpectedly on physics in the first part of the 20th century. Okay, now it's kind of funny because special relativity landed in 1905. Just before that time, there was a physicist named Albert Michelson, an American. He was, I think, the first American to win the Nobel Prize in physics. So no, he was no slouch. He was a solid person. He knew what he was doing. And Michelson said in 1903, talk about your famous last words. This is what he said. This is a very famous quote. The more important fundamental laws and facts of physical science are now so firmly established that the possibility of their ever being supplanted is exceedingly remote. Future discoveries must be looked for in the 6th decimal place. What Michelson was saying was, hey, we've got this physics stuff so nailed down, so figured out that, that the only refinement we're ever going to make to this stuff is by measuring like the gravitational constant better, or measuring Coulomb's constant better, the constants, of proportionality that are in those equations. We can measure them better, so we have more, better values, but we've pretty much wrapped physics up. That absolutely turned out to be completely wrong. I imagine that Michelson probably laughed about it later on, because many people have been just amazed at how ironic it was that he would say this just before the first of our three revolutions hit physics in the beginning of the 20th century. Well, we're going to take one step back again to recall Galileo, and that's going to help us understand how the study of light gave rise to what's called special relativity. Okay, remember Galilean relativity. Let's suppose you've got someone on a train, and the train is moving to the right at 10 miles an hour. Now, let's say the train is moving at 10 miles an hour to the right relative to the ground, okay? And let's say that the person on the top of the train is also walking on top of the train at 5 miles an hour. Okay, well, what is the velocity of the person relative to the ground? So from our Galilean relativity that we studied before, we know that we just add these two numbers together. The train is moving at 10 miles an hour to the right. The person is moving relative to the train 5 miles an hour to the right. So relative to the ground, the person is moving 15 miles an hour to the right, which is 10 plus 5. That's how it works. Okay. Now, let's add a little wrinkle. Okay. The speed of light we talked about before, by the way, I should point out that it's really fast. The speed of light that shows up in Maxwell's equation and had been measured several different ways by the time of Maxwell. The speed of light is extremely fast. That's why we don't notice a delay when we turn on a light switch. The light travels to us so quickly that we don't perceive a delay. Light actually travels in miles per second. It actually travels at 186,252.8 miles a second. So, like on the highway, typically people go like 60 miles an hour. 60 miles a second would be 3,600 times as fast. But this is not 60 miles a second. This is 186,000 plus miles each second. So the light from the sun to the earth, which is 93 million miles away, takes 8 minutes to get here. But that's really fast compared to anything in our everyday experience that we can perceive. Okay, so that was known to be the speed of light. It was measured. It was found to be that before, pretty much that value before Maxwell's equations. And Maxwell had, from his equations, been able to show that an electromagnetic wave, which would move exactly that speed, and so it had to be light, and it was, as well as there were other wavelengths that we couldn't see, but so electromagnetic waves move at the speed of light. And So now let's turn our attention back to the person on the train. Let's say now the train is still going 10 miles an hour to the east. But in addition to that, the person, and let's say the person's now standing still on top of the train, but the person has a flashlight and they're shining their flashlight to the right. Okay, so the question is, if the train is moving 10 miles an hour to the right, and the light from the flashlight is moving, relative to the train, because the person's on the train, the flashlight's being held by the person, and so the person's, not moving relative to the train, the flashlight's not moving relative to the train. But if the light leaving the flashlight is traveling at the speed of light, let's just call it c, because it's such a big number. What is the speed of the light relative to the ground? If the speed of light is c relative to the train, what is the speed of light relative to the ground? Okay, now we just talked about, if you had someone walking on the train at 5 miles an hour and the train's going 10 miles an hour, then the speed of the person relative to the ground would be the sum, right? And so if this works the way Galileo said, we would expect that the speed of the light leaving the flashlight relative to the ground would be not c, but c plus v, the velocity of the train. So we'll say v is the velocity of the train. So if c is the velocity of the light relative to the train, then relative to the ground, the velocity of the light would be v plus c. Well, that's not what Maxwell's equations say. Maxwell's equations say that light moves c, just c. All right? So there was a lot of confusion among physicists about, in Maxwell's equation, what the speed of electromagnetic waves was relative to. Was it relative to the source of the light? Was it relative to the medium the light moved through? And let me tell you what I mean by medium. If you have a guitar string and you pluck it, you get a little vibration on the string. You have a little wave that moves along the string that produces sound. That string travels along, that wave, that vibration is on the string. The medium of the little vibration of the little it's called a mechanical wave that moves along the guitar string is the string. If you have sound in air, it travels through the air. If you're in space in a vacuum, you would not have sound. There needs to be something for the sound to travel through. That's a compression wave, where the wave is actually an oscillation, a variation in pressure up and down, and that's what sound is, a traveling pressure wave. Okay, if you have ripples on a puddle, what is the wave traveling through? Well, it's traveling through the water. Those things are called the medium of the wave. And so physicists understood waves since the time of Newton. Newton had it mostly figured out, at least as far as waves. And then, Young figured out that light was a wave. And so physicists figured that there must be some medium that light moves through, just like every other wave they knew about. And apparently in Maxwell's equation, that c thing that comes out of the equation, the speed of light or electromagnetic waves that comes out of the equation, that must be relative to the medium, because every other equation that physics had come up with, where they came up with the speed of sound or something, all those equations gave the speed relative to the medium, okay, the thing that the wave traveled in. So it was thought that light had to travel through a medium, and apparently Maxwell's equations, which only give one speed of light, that speed must be relative to the medium, okay? But the thing is, we know some things. By this time, scientists understood that as you traveled higher and higher in the Earth's atmosphere, the pressure would become lower and lower until eventually, when you were high enough up, essentially you would be in a vacuum, the vacuum of space, and it wouldn't be too far from the Earth where that happened. And that's why the moon didn't eventually spiral into the Earth, because there was no friction with the air that would cause it to lose speed. It was in a pretty good vacuum, the moon and the other heavenly bodies. So space had a vacuum, but you know what? We still see the stars, we still see the moon, we still see the sun. So the light that we see from the sun and the moon and the stars, that seems to travel through the vacuum, right? So if there's no air, what is the light traveling through? Well, scientists had no idea. They figured it had to be something, and that must be the thing that the speed of light is measured against, right? That must be the thing, that there must be something that light travels through, and that's what Maxwell's equation is talking about when it says the speed of light is this value c. But it can't be air, and there's nothing physical that we can see. So they didn't know what it was, but they gave it a name. So if you can't do anything else, you give it a name. And they went all the way back to Greek times. Remember when Aristotle supposed that there was, in the realm of the heavens, in addition to the four Greek elements, earth, wind, fire, and water, that there was also something called the ether that the heavenly bodies were made out of, and he thought that would be something that glowed. Well, they borrowed that term from Greek history, and they figured, okay, we don't know what the medium of light is, but it has to fill space because light travels to us from the sun, from the moon, from the stars. There must be some medium that these waves go through, these electromagnetic waves, and that must be what the speed of light is relative to. Okay, so they figured this, that just kind of like our person shining a flashlight on the train, if you're on the Earth, okay, and this ether fills all space because we can see things from all these heavenly bodies, the Earth itself must travel in some direction at any point in time through this mysterious medium called the ether. Okay, because the Earth rotates on its axis and it revolves around the sun during the year, and even the sun is traveling itself. So as the surface of the Earth changes its position, the direction it's going in as it rotates and revolves, and the Earth itself revolves around the sun. It must be changing, constantly changing its position relative to the medium that light travels in, which is called the ether. So Michelson, who made this famous quote, who said that if that physics is just going to be about precise measurement, he decided that he was going to come up with a very way to precisely measure the speed of light, so he could figure out that the light was traveling at different speeds on Earth depending on which direction the light was going in, because the whatever current was in the ether, whatever relative direction the Earth was moving in the ether, if you took the ether to be kind of still, or if that's the same as thinking the Earth is still, and then what the ether is moving in one direction or another, whatever the relative movement of the ether is compared to Earth, or the Earth to the ether, the apparent speed the light would be traveling relative to the Earth would be just a little tiny bit different, depending on whether it was measuring going in the same direction as the ether, or where it was going opposite the direction of the ether, or kind of right angles. And he came up with a very precise way to measure things, and it was called an interferometer, and it's the most precise way we can measure anything. This is what he eventually won the Nobel Prize for, because it's used, it and variations of this are used in so many physics experiments now to measure very precise distances. It can measure things up to a billionth of a meter, not the nearest centimeter, not the nearest millimeter, not the nearest millionth of a meter, but the nearest billionth of a meter, which is good enough to help measure how many wavelengths of light there are in a particular distance. And because the wavelength and the speed are related of any wave relative to say to a fixed space on the ground, that can kind of be used to tell you the speed of light. And so he came up with an arrangement where he had light, and there was like a half silver mirror that basically allowed half the beam of light to travel on and the other half to be reflected. And so he had two mirrors, and he could adjust the positioning of the mirrors, and he could figure out how many total wavelengths was in any particular path. Okay, because he could change the position of the mirror, and he could observe based on the pattern of the waves, how every time he crossed a new wavelength of light, he could kind of figure it up, and he knew the frequency, he knew the wavelength of light based on the color, and that basically allowed him to figure out the speed. And he had a partner in all this, another scientist called Morley. So this is called the Michelson-Morley experiment, and they went to great efforts to set up this experiment, and it was on a huge slab of stone floating on a tank of mercury that would isolate it from any movement or any kind of vibrations or anything. And they spent considerable time running and rerunning this experiment, expecting to find that in some directions the speed of light was just a little different than it was in other directions along a particular path. That's what they expected to find. And they did not find that. This experiment became known as the most famous negative result in all of physics. It did not appear, they simply were unable to find any evidence whatsoever that there was ether that was moving relative to the Earth in a particular direction. They found no evidence of the ether. Okay, and so no matter where they looked, no matter what direction they looked in, light seemed to travel at just the same speed that Maxwell said it should. Okay, so back to our train experiment. How can we explain this? If the speed of light travels c from the flashlight, which is on the, which is not moving relative to the train because the person is just standing still holding the flashlight, how can the speed of light be different on the ground if it's not what is the speed of light measured relative to? Is it measured, if it's relative to the flashlight, is it relative to the ground? Maxwell's equation says nothing about the speed being relative to anything. The whole ether thing, the whole medium that light was moving through was just a guess, that there must be a medium. So it's really perplexing. And then in 1905, Einstein said, at the time he was working in a patent office in Switzerland, I think, he said, what if we take Maxwell's equation seriously, and we just suppose that the speed of light is seen to be exactly c, this big number c, 186,000 whatever, exactly the same number no matter who's measuring it. In other words, what if the person holding the flashlight measures the speed of light to be exactly c, and the person on the ground would measure that to be the same? Well, that seems a little wacky, because how can it seem the same? But the person is moving relative to the ground because the person is on the train, and the train is moving at 10 miles an hour. So how can the person on the ground think the light is traveling the very same speed that the person on the track is, the person on the ground is seeing. If you suppose, like Einstein, that both observers would see the same speed of light, that seems hard to reconcile with Galilean relativity and Newtonian physics, which is kind of built on that. Okay, well, it turns out, and this is weird, Einstein was correct. Einstein was correct, and Maxwell was correct, that the speed of light is c, period, as long as light is moving through empty space. It's a little bit different in a lens or something. Maxwell's equations describe that too. But if light is just moving through space, it's c. It's just c. No matter what the relative motion of the observer is to the light, or no matter what the source of the light is, how the source of the light is moving relative to the observer, the speed of light is always observed to be c, just like Maxwell's math said. So what gives? Well, it turns out Newtonian physics kind of breaks here. It changes. The rest of physical reality is different than what Newton thought because of this. Okay, so the speed of light, and remember, speed, which is velocity, the size of the velocity, is in length per time. It turns out that in order for the speed of light to be agreed upon by everybody, it turns out that different observers actually would measure time and length differently. So in order for Maxwell and Einstein to be right, the observers no longer agree. They agree on the speed of light, but they no longer agree on lengths and times. And this turns out to be correct. So we talked about earlier in our course about timekeeping, and early in the scientific era, there were pendulum clocks and spring-based movements that allowed a certain timekeeping where each tick corresponded to a certain interval of time. And then, later on, quartz crystals were discovered, and it turns out that they can be, powered by a small battery and caused to oscillate, and they can each little oscillation of the crystal, each little vibration in that crystal can correspond to a little interval of time, and the time is much more accurate. We've even come up now with what's called atomic clocks that are accurate to 1 second every 40 billion years. So extraordinarily accurate clocks, and we're even going beyond that now with something called a nuclear clock that's in the works. But we have extremely accurate timekeeping. But in order to establish the theory of relativity, Einstein thought of a whole different type of clock, and this is a theoretical device. Okay, he came out with something called a light clock. Okay, now his light clock is what's called a thought experiment. Einstein famously had these various thought experiments that helped him to kind of think through the implications of certain things, like the speed of light being the same for everybody. And so here's what Einstein did. He figured, okay, there are a lot of ways you can keep time. Let's suppose you have a pulse of light that's bouncing back and forth between two mirrors at some particular distance, L. Okay, so this pulse of light bounces back and forth, and let's say every time the pulse gets to A, the mirror at the bottom, every time it gets to A, we'll count that as a tick of the clock, and it'll correspond to a certain amount of time. Okay, so we know the speed of light is c, and we know the total distance the pulse of light travels as it goes up to B and then back to A is twice the distance between A and B, because it goes up and back. And then we divide the distance by the speed, like we talked about before, and we get the amount of time each tick takes, each little pulse, each little tick of that clock takes. We could make our clock work on this in theory. Okay, so Einstein said, okay, let's suppose we have a light clock. Now, to study how this, to study how light behaves to two different observers, let's put our light clock on the train. So take off the guy with the flashlight. Now we're going to put our light clock on the train. Okay, so to people on the train, their light clock works just like they would expect. The light pulse reflects from A to B, and then it reflects back to A and just bounces back and forth. And so you get exactly the behavior that we've explained. And so that's what powers your timekeeping. The little pulse of light going back and forth, up and down on your between those two mirrors. But let's now think, how would it look from somebody on the ground? Remember, the train is traveling 10 miles an hour to the right. Okay, so that means that the light clock on the train is traveling to the light. Okay, and so rather than moving up and down, it almost looks like as the train travels, to somebody on the ground, it looks like the light is going kind of up at an angle to hit the mirror, and then it's reflecting back down at an angle to get back, to get back to A. So it's going from A to B to A, except it no longer looks like it's vertical, up and down. The mirrors still appear to be separated by the same distance L, but now the light is traveling further, at least as observed by a person on the ground. And if the person on the ground continues to see the speed of light, continues to observe this, measure the speed of light the same, but now is seeing the light traveling a longer total distance, 2 times the, which, because you can see that the distance there, D, as you go from A to B, and then from B back to A, as the mirror is going to the right on the train, as the person on the ground sees it, that distance is bigger than L. So the time it takes for the light to travel the greater distance, since the person on the ground is still seeing the light traveling at the same speed, that the amount of time there is greater. Okay, so a person on the ground thinks that the light clock on the train takes longer to tick. Okay, and the inference Einstein drew from this was that time appears to move slower on the train relative to someone on the ground. Okay, now you're probably saying, get real. This is just a math trick. This is a pretend clock. It's not even a real clock. And you're saying that, give me a break, this doesn't prove that time goes slower on a moving train. Okay, well, it turns out it is true. The faster the train moves, the more significant the difference is. It turns out that if the train, you wouldn't really even notice the difference until the train starts moving more like a third of the speed of light, or 4/10 or 5/10 of the speed of light. But eventually, if the train itself is moving faster and faster and faster, the difference between how time flows on the train relative to, from the reference of some, as seen by someone on the ground, the difference is huge. So if you get up to like if you get up to like 9/10 of the speed of light, if you get the train going really fast to the right, like 9/10 speed of light, which is unrealistic, we can't make things go that fast, but if you did, okay, it turns out that every second that ticked by on the ground would actually take 2.5 seconds or so to tick by on the train. In other words, 1 second on the train would appear to require something like 2.5 seconds on the ground. So from the perspective of someone on the ground, if the people on the train got a year older, the people on the ground would actually be 2.5 years older. Now this is absolutely bizarre. It seems totally unreal, but this kind of thing has been very well measured. Okay, it turns out even our GPS system has to take this effect into account. With the satellites that go around the Earth, there's some other effects that have to be taken into account too, because general relativity also has something to do with how time flows. But let's take a simplified example. Okay, let's suppose that you're not on a train now, but you're on a rocket ship, and somehow you can travel at almost the speed of light, at like, just 99.9% the speed of light to the nearest star, which is 4 light years away. In other words, the amount of time that it takes light 4 years to travel. So from Earth, it seems to take 4 years. Your rocket ship seems to take about 4 years to get there, just over what light would take, because you're going almost but not quite the speed of light. But on the spaceship, you would only experience 2 months. So each second on the ship, each second that goes by on the ship, you would correspond to almost half a minute going by on the Earth. Well, we could ask another question. On the spaceship, how far away does the nearest star look? Because from Earth, the nearest star looks like it's 4 light years away. On the spaceship, it only seems like it's 2 light months away. So only 140, it only seems to be about a 24th or about 4% of the distance that it seems to be from Earth. So not only does the flow of time change depending on how fast one thing is moving relative to another, but also the different observers and the different in relative motion to each other would see lengths as being different. So what looks like 24 trillion miles on Earth would only look like 4% that far from our rocket ship. This seems absolutely crazy, but it's a real thing. And it comes from taking Maxwell's equation seriously, that the speed of light is always what's measured for any observer. Well, here's a pop quiz for you. If we said vice versa, what about the person on the train? How? Let's say there's also a second light clock. Let's say there's a light clock on the ground. What would a person on the train see? And at this point, you're going to be ready to tell me I'm just completely contradicting myself. But it turns out that the person on the train would think the person on the ground the time for the person on the ground would be moving slower than for them. So they would measure the same thing because there's the same relative motion, and that seems to be a contradiction, but it isn't. It's a paradox that eventually we get kind of straightened out when we understand what's called general relativity, because it turns out you have to take into account gravity and accelerations, and once you do that, you can realize that in fact the person on the spaceship would have the solar clock in net. If you started off from Earth, you sped up to that speed, you went to the nearest star, you turned around and came back, you would have aged very little compared to, say, your twin who was left on Earth, and they would have aged much more. So time and space change in order in just such a way that the speed of light is measured to be the same by all observers, and that is special relativity. So yeah, that's what happens. Now, is there any difference in what the observers do see? And the answer is yes, there is a difference. The different observers, like the person on the train with the flashlight versus the person on the ground, they would see that light was traveling at the same speed, but they would perceive, the person on the ground would see that the frequencies of the light had shifted compared to the person on the train. So the light would look like it had a different spectrum. Okay, and this is similar to the Doppler effect that we observe with sound. Like if an ambulance is approaching you, remember sound is also a wave. The pitch of the ambulance seems higher until just the moment it passes you by, if you're on the sidewalk right next to the road, and then it seems to shift to a lower sound. That same kind of shift occurs when the source of the light is in motion relative to you. You see a shifted spectrum, but the speed of light is the same for all observers. So here's a picture just kind of showing the Doppler effect there, and the math is a little different, so it's kind of an analogy. It's not a perfect analogy, but it's very similar. So space and time are relative. That's what Einstein figured out. But remember what physics is? It's the study of mass, energy, space, and time. So if you're changing what space and time actually are, depending on your reference frame, what else changes in physics? What about forces and momentum and mass and energy? Well, the laws, in order for the laws of physics to hold, our conservation laws to hold for all observers, relative to any observer, it turns out that everything else has to change too. So the different observers see different size forces, different sizes of momentum, and they even see different mass and energy. Because clearly, if I'm on the train moving relative to the ground, and I throw a ball, it seems to be traveling at a different speed to me than the person on the ground. Unlike light, they actually do see a difference in the speed of the ball. But, and so I would measure a different amount of kinetic energy. Well, it turns out in order to have conservation of energy hold, it's as if the mass, which we would kind of think of as the weight, the mass, the amount of stuff, that gravity is attracting, which we measure by weight, that mass has to change in order for the conservation laws to hold. And it's as if mass is equal to a certain amount of energy. So before, we talked about how early chemists, like Lavoisier, had found that in a chemical reaction, essentially, if you kept things in a container where a chemical reaction happened in a container, even fire or whatever it was, that the total mass didn't appear to change. And we've talked about energy appears to be conserved, and that becomes one of the basic ideas going all the way through thermodynamics, which we talked about. But it turns out according to Einstein, energy and mass cannot be separately conserved. Depending on the particular reference frame, depending on how fast one observer is moving to another observer, in order to have conservation, you have to figure out the sum total of mass and energy. So all of this coming from, Maxwell's equations. It really, and so as something moves faster and faster, its mass appears to increase. So this I'm not going to help us to see even in a simple case. I'm just going to say this is kind of the way it is. This is because you need math to get there. But it's just like with time dilation or length contraction. You an object, as it gets faster and faster, appears to be more and more massive. So in order to keep a conservation to the total amount of mass and energy, we get to Einstein's famous equation. The energy related to a particular mass is mass times c squared, the speed of light squared. And that c, remember, is a huge number. So a little mass is equivalent to a lot of energy. And in fact, it suggests that mass and energy may be kind of like the same thing. And indeed, later on, it turns out that from energy you can create mass, and from mass you can create energy. There are some real world consequences of that. One of the real world consequences is if you take a little bit of mass in an atomic bomb and you turn it into energy, you get something that we're all rightly concerned about. You get the potential for huge destruction because it's a little mass can be turned into so much energy. It's insane. A relatively small nuclear device, which might weigh a few hundred kilograms, right? Say that's maybe a hydrogen bomb that can be put on a missile and launched to the other side of the Earth. That relatively small device may only convert a fairly small percentage of its mass into energy, and just that conversion can be equal to millions of tons of TNT, which is a high explosive. So you could take a whole ton of TNT, that would be 1 ton of TNT, all the chemical energy released in an explosion, which I mean, talk about a ton. You could blow up half the city of Chicago, or blocks and blocks of the city of Chicago with 1 ton. Just a few kilograms of mass turned into energy can actually be equivalent to the amount of energy released by a million tons of TNT. So effects. Well, it turns out special relativity messes with us even more. It happens that different observers are going to have different ideas about when things occur. And maybe that shouldn't be too shocking because time seems to be different between the two observers. So let's imagine that we've got a train moving to the right and a person standing in the middle of the train. We'll call that person M. There's a person on the ground, person S, standing still relative to the ground. And just when the train is right between two electrical poles, on the left L and on the right R, as seen by the observer standing on the ground, observer S, lightning hits the two telephone poles. Okay. Observer S on the ground would say the lightning flashes were simultaneous. They happened at the same time. The person on the train would not say that. The person on the train would see the lightning from the right first because they are traveling toward it, and they would see the lightning that hit the electrical pole on the left second because they're traveling away from it. It'd be a very slight difference, but the point is that the observer on the train would think that the lightning flash that hit the right telephone pole actually occurred before the lightning flash on the left. So at the exact moment as the train is midway between the two when the lightning hits, the observer on the train would believe that the lightning flash hit on the right before the observer on the ground thought the same thing. Then the observer on the ground would think the lightning had hit on the right as well as the left, and then the person on the train finally would think that lightning had hit the electrical pole on the left. So in the present moment, in that moment, the observer on the ground would see the lightning flashes, but that same moment would not be experienced in the same way by the person on the train. The person on the train would experience the lightning hitting the electrical pole on the right in the past, when the person, at the same moment when the person was lined up with the person on the ground. And they would also experience it. They would have to wait a little longer at that moment to see the flash of lightning on the left. So in other words, that exact moment when the train is passing, the person on the ground, what they experience as the present would actually, part of it would actually be in the person on the train's past, and part of it would actually be in the person on the train's future. So this is kind of amazing. Sounds wacky, I know. It's just my future is now for somebody if they have the right relative motion toward me. Okay, and my past is also now for somebody if they have the right relative motion for me. Um, so this sounds completely nuts. There are ways of picturing this, um, and and it's something that we may explain later when we get to general relativity. But for now, just keep that in mind. My present moment could be in someone else's future, but it could also be in someone else's past. Okay? That's pretty profound because, we tend to think of time as existing just in the current moment, right? It's kind of like, okay, we know we think the past existed, but it isn't there anymore. It's just the current time is there, and we think the future will exist when we get there, but then this moment will be lost, kind of like the view on the left. But the way special relativity causes us to think about time and space is different. Because my current moment is somebody's past, and because my current moment that's real to me right now is someone else's future, it suggests that really the past, the future, and the present, they all still exist in a certain sense. And this idea, physicists called the block universe, that all times are equally real. In some ways, it might be how God sees things. We know that God knows the past and the future, and the Bible says He calls the end from the beginning. Well, if He sees the entire block universe simultaneously, that kind of fits with what relativity tells us about how the past and the present are still real. They're still there, and God sees it all at once. So He sees the entire block universe at one time, the past, present, and the future. And in fact, we would say that He shaped the block. It's His block. He made it. So it's pretty cool to think about that, although pretty pretty mind-bending. A lot of questions arise, right? A lot of questions arise because the space and time we experience is a matter of our perspective as determined by our location in space and time and how we're moving through it. So, yet we can't say that it's our subjective point of view, because anyone else in the same place with the same relative motion would agree, on distances and times and order of events and things, but different observers don't agree. So everything is relative to where you are and how you're moving. Um, and so, is God bound by the time we experience, or is God above it all, like seeing the block universe all at once? And we can ask questions at this point without going too much into them. But does it make sense to talk about before creation? Then, is there time and eternity? How long did creation take? Could that have been affected by your perspective? So I'm just going to throw those questions out there, and for now, I'm going to say let's just take our conclusion for the moment from the song "I Can Only Imagine." Okay, all this stuff is very profound, and maybe it could give us some insight into how to even look at God's Word and think about how God sees the universe that He created. Well, um, I have a little kind of a meditation here for us. Um, and I'm just going to, kind of to respond to what we've gone over today, at least how I responded to it. And so I hope you'll enjoy it. It's called Creator God, Light of the World. Master of space, time, matter, and energy. Able to mix and mold them as you choose. You chose the cross to give us new hearts and a hope we do not refuse. Wondering what we become with eyes on you. In your light, we know the way ahead. In your light, we see truth. In your light, we have bright lives. But it's in your love that we have light. Well, I hope you've enjoyed today's class. Next time we're going to get into or closer to some wild and wacky stuff. We begin to get into quantum mechanics, and we'll end up seeing how physics and chemistry, kind of connect in a quantum world. It actually may take a couple of classes for us to get all the way there, but thank you for listening, and see you next time.